Topic 13.6 Equations of motion in cylindrical and polar coordinate system. Chapter 13. Equations of motion cylindrical coordinates. Today's objective is to analyze the kinetics of a particle using cylindrical coordinate system. Remember, we use cylindrical coordinate system when particle has a three-dimension circular motion. For example, spiral slide as shown in the figure. The normal force which the path exerts on a particle is always perpendicular to the tangent to the path. When the force acting on the particle are resolved into cylindrical components, friction forces always act in the tangential direction. Sorry, the correct answer is transverse direction, not tangential direction. The force acting on the 100 pound boy can be analyzed using the cylindrical coordinate system. So if we consider the boy as a particle, then define the axis, then this is the radial direction of the axis. This is transverse direction or theta of the axis, and then this is z direction of the axis. So we have set up the cylindrical coordinate system that has r, theta, and z axis. And now we can include the different forces in our free body diagram, such as weight of the boy along the z direction and the normal force depending on the angle of the slide he experiences. Plus, if there is any friction force that will oppose the direction of motion, that will be in this direction F. So how would you write the equation describing the frictional force on the boy as he slides down his this helical slide? And for that, we need to apply the equation along the transverse direction theta. So we will write this equation: sum of forces along theta is mass times transverse acceleration, a theta. And then in this part of the equation, we will include the frictional force. And a theta can be calculated using kinematics that we have studied in chapter 12. Second application, when an airplane executes the vertical loop as shown, the centrifugal force causes the normal force, which is also called the apparent weight, on the pilot to be smaller than her actual weight. How would you calculate the velocity necessary for the pilot to experience this weightlessness? So the forces act along the radial direction of the motion. So we will apply this equation: sum of forces in radial direction is equal to mass time radial acceleration. And the weightlessness happens when there is no contact between the body of the pilot and the seat supporting her. So for that, the normal force will be 0 for weightlessness. And it's same as you are in an amusement ride, and then at some point you feel that you are being lifted off the seat, and at that time we feel like weightlessness because there is no normal force. There is no contact with anything surrounding. And that's why the only force that is responsible for at the time is the weight force, mw equal to mar. And by calculating ar using the kinematic equations, we can calculate the required necessary parameter for this problem. So cylindrical coordinate system we use where we define three axes: radial axis, transverse axis theta, and z for particle having three-dimension circular motion or three-dimension curvilinear motion. So, and then for each one of these axes, we can write down corresponding equation of motion, such as sum of forces in radial direction is equal to mass times radial direction. And in chapter 12, we have studied that radial acceleration can be calculated using this equation. Sum of forces along transverse direction is mass times transverse acceleration, which is calculated using this formula. And sum of forces in z is equal to mass times z acceleration. Remember, z double dot is nothing but d square z divided by dt square. It's called acceleration along z direction. So these three are our equations of motion for cylindrical coordinate system. If it is polar coordinate system, then we do not have z-axis, and at that time we use only r and theta, and these are the two equations of motion for polar coordinate system. And in the next video, we will solve a problem using cylindrical coordinate system.